I'm Hal Weber. I'm a trainer for Eiffel Software. You probably know me from such memorable presentations as Eiffel, an Introduction, and Design by Contract, Part 1 and Part 2. In this presentation, I want to talk to you about how Eiffel the language differs from C#. So here we'll be speaking of Eiffel the language versus Eiffel the development framework, and we'll be looking at programming language features. Of course, it would be impossible to do a comprehensive comparison of C# and Eiffel in the few minutes that we have, so I'll just try to touch on those points that I think are the most important to most software developers. At Eiffel Software, we're proud of the features of Eiffel that are not in most languages, like design by contract, multiple inheritance, genericity, and covariant modeling for routines and generics. But what you'll find out in this presentation is that the reverse is true as well. That is, to Eiffel's credit, there are lots of things that Eiffel does not have. I think you'll be impressed with how much simpler Eiffel is than C# while providing more functionality. Remember that you can use the navigation controls to skip around in the presentation if you need to. For example, if you view the Java presentation after the C# presentation, you may want to skip some of the syntax differences in the Java one because of the syntactical similarity of Java and C#. So here's what we'll cover. First, a bit about Microsoft.NET and the origin of C#. Next, we'll look at some of the differences in syntax. And third, we'll look at a few other language features, things that the Eiffel language has and C# doesn't, and vice versa. So first, let's talk just a minute about Microsoft.NET and C# in general. Just in case you didn't already know, Microsoft.NET is an important innovation. Now, I used to hear some folks dismiss .NET simply as Microsoft's answer to Java. I think that's selling .NET way short, and I'm not hearing much of it anymore. Although Microsoft may have been pressured by Java competition to produce .NET, and what they produce bears some similarity to Java, .NET is also very special in its own right. How? Well, like Java, .NET introduces a common object model that contains some of the elements of good object orientation, like inheritance and dynamic binding by default. The .NET framework includes a massive set of useful type libraries based on this object model that covers many areas of common computing needs. There are libraries oriented toward GUI programming, web servers and applications, XML and web services, Windows services programming, data access, and the list goes on. Even from the very first release, .NET has included powerful tools built on these type libraries. ASP.NET, just as one example, revolutionizes Microsoft's support for web servers, applications, and services. But one thing that makes .NET truly unique and extraordinary is its unprecedented levels of language interaction. The types available in .NET's included type libraries, or for that matter any type library created using a compliant .NET language, are potentially accessible and reusable directly by software written in the same or any other .NET compliant programming language. And there are over 20 such languages, Eiffel of course being one. This gives computing professionals powerful economic leverage if only they will choose to use it. Let me try to give you an example of how powerful this is. Suppose you had a lot of legacy engineering software originally written years ago in Fortran for mainframe or mid-range computers. You don't want to keep the old computers and operating system, but you still need the functionality that the software provides. If your eventual goal was to live in the Java world, you'd embark upon a massive effort to convert all the old Fortran to Java. But with .NET, you might be able to save a lot of time and money just by adapting your software systems to run under .NET using a Fortran compiler available for .NET. And another example, suppose you're building systems in your favorite .NET compliant language, say Eiffel, and you want to build a class that inherits from a component that first was written by someone else in some other language, C# maybe, and second, for which you only have a compiled version. In .NET you can do exactly this. So the language interaction available in Microsoft.NET surpasses anything we've seen before, and it holds the potential for great economic gains by prolonging the life of legacy systems and raising software reuse across languages to unprecedented levels. Like C#, Eiffel has been available for .NET since the initial release of .NET. Also like C#, as a .NET language, Eiffel is fully compliant with .NET's Common Language Specification. When Bill Gates made the initial .NET announcement at the PDC in July of 2000, Eiffel Software's Chief Technical Officer, Bertrand Meyer, stood with him to announce Eiffel for .NET. Since then, the Eiffel implementation on .NET has continued to improve. Eiffel Software is a Visual Studio integration partner. Our Eiffel Envision product is a plug-in for Visual Studio .NET. With Eiffel Envision, you can develop Eiffel projects in Visual Studio .NET in the same Visual Studio solution as projects written in other .NET languages. For the Microsoft community, .NET ushers in a new, more consistent computing model based on object orientation. Once committed to this model, Microsoft had decisions to make about their programming languages. Essentially, there were three options. First, they could rework their old languages to comply with the new model at the expense of compatibility with some legacy code. Second, they could adapt their old languages with extensions which would allow compliance with the new model while maintaining compatibility with old non-compliant code. Or third, they could design a new language based directly upon the new object model. And in fact, they exercised all three of these options. Visual Basic was altered for .NET, but code written under previous versions will likely have some compatibility problems requiring attention. Still, despite the conversion pain they may cause, most of the changes to Visual Basic inspired by .NET are for the better. C++ was extended to support .NET by adding a set of managed extensions, but while maintaining compatibility with older code. And the new language, of course, is C#. Among other things, C#, like Java, uses a syntax based on the C programming language. Java mimics C for the sake of familiarity, so that programmers who had gone through the arguably difficult process of learning to program in C or C++ would not have to learn something completely different. Java and C# do remove some of the really pathological features of C and C++, and mostly this stuff won't be missed. And that's all good, but still they retain some of the, how should I say this, less elegant design decisions that were part of C. These things are things that weren't good in the beginning, and they're still not good. Of course, I'm not saying that programmers can't get used to dealing with these idiosyncrasies. They can. But that doesn't make them good, and they cause new programmers to have to go through a long learning curve and deal with unnecessary problems, and that costs organizations money. I spoke to a programmer recently who had moved from VB6 to C#, and even though he had been using C# for over a year, he said he still occasionally left off a semicolon, or forgot to put the empty parentheses after a call to a function with no arguments. Now let's talk about some of the syntactical differences between Eiffel and C#. And you'll probably notice that it's a little hard to talk only about syntax without getting a bit into language semantics and culture as well. So although this section is primarily about syntax differences, it also slops over some into the effects of language syntax on programming practice. In object-oriented programming, we use declarations to define class features or members, as well as local entities. So by using a declaration, we say, for example, I have a thing called hour, and its type is integer. C# follows the C pattern of declarations, specifying the type first. The problem with the type-first approach in the C family of languages is that we don't ordinarily go looking for declarations in code by their type. Usually we're looking for them by name because we're reading some procedural code and we see the name used there. Ian Joyner, author of the book Objects Unencapsulated, likens the C style of declaration to having a dictionary in which the entries were listed by their part of speech. So you'd look down the left-hand side of the page and you'd see noun, noun, adjective, adverb, etc. This just doesn't make much sense. But that's the way it was in C, and so that's the way it is in C# and Java. To add to the confusion even more, in a declaration, the type could be preceded by .NET attributes and or modifiers, things like public, sealed, or static. Eiffel specifies the entity name first, then the type, similar to the way it's done in mathematical notation and in some other programming languages. Because the name appears first, declarations are easier to find. Another thing you might want to take note of is a difference in the syntax for comments. In C# you can use the double slashes like in C++, and comments for declarations usually precede or share the same line with a declaration. In Eiffel, use the double hyphen. The comment you see here is called a feature header comment, and it always occurs immediately after the line containing the feature name. Eiffel Studio is sensitive to the presence of header comments and will include them with consumer views of the class. The assignment operator in C# is the equal sign. In Eiffel, it's the colon equal. The equal sign is used for test of equality in Eiffel versus the equal in C#. In C#, blocks of code are enclosed within braces, and you can code blocks of code within blocks of code. This is done often to isolate scope for local variables. In Eiffel, this isolation of scope is done through the routine calling mechanism. So there's only one block of code and one set of local entities per routine. This means that Eiffel routines are usually quite short, and that's a good thing. Remember, complexity is the greatest enemy of reliability. A few very long methods or routines are harder to manage and more error-prone than a few more short routines. Also, if you've seen the design by contract presentations, you'll know that Eiffel programmers specify what our software does at the routine level by coding declarative contracts composed of assertions. This becomes more and more difficult as a routine's length and complexity increase. Another problem with the braces is that they add additional syntactical elements to deal with, which then makes it more difficult to settle on a common coding style. Where do you put the braces? How do you indent? Try this. Do a Google search on C# style. You'll find so many style guides and forums that you'd think there must be one for every 3 or 4 programmers. And when you read them, you find out that they offer varying advice. Contrast that to Eiffel, in which most programmers tend to agree upon a single style to which everyone seems to gravitate naturally after using the language a while. And to make things even better, if you want to see a view of any class in the currently accepted Eiffel style, all you have to do is look at its clickable view in Eiffel Studio. This view is generated from the Eiffel compiler's abstract syntax tree, not from the text file. As a result, Eiffel Studio generates the clickable view of any class in the accepted format. One more thing you should notice here is the use of the semicolon. It's required in C#, a terminator following each statement. The semicolon is defined in Eiffel, but as a separator and is optional in most cases. But whether it's considered a terminator or separator, we should view it only as useful in 2 cases. First, it may be necessary to make the compiler understand our routine, and second, it may be helpful to human beings attempting to understand our routine. The first case is quite rare. The second case is rare too if we code one statement per line, as we see here. But this code could be written all on a single line like this. In this case, although still optional to the compiler, the semicolons would help readability, like this. But most Eiffel programmers usually code one statement per line and leave the semicolons out, which, not surprisingly, is what the clickable view looks like. Both C# and Eiffel use a dot notation for calls to routines. But when you call a routine that takes no arguments, as in this C# example, you have to include the empty parentheses after the routine name, indicated here at the arrow. But in Eiffel, you never have to include a set of empty parentheses. Here's the equivalent code in Eiffel. C-sharp's if structure requires parentheses around the conditional expression. The corresponding code in Eiffel does not require the parentheses. The C-sharp code that gets executed as a result of the condition being true is enclosed in braces because it's a block of code. In Eiffel, the code to be executed in the true case is between the then and end keywords, producing a more naturally readable form than the C-sharp. It's interesting to note with this particular case in C-sharp, the braces aren't strictly required because the code is only one statement. So the C-sharp example could look like this. But the C-sharp rules are more complicated than just that. What if we did this? It's still just one statement, but it produces a compile error. Why? Because it's not an embedded statement. Of course, it's a little silly anyway, because even if it were valid, the local variable greeting would get created but would never be used. But here's the same silly thing in a form that's perfectly all right with the compiler. Many languages, C-sharp included, carry with them unnecessary complexity. Sure, you can learn to deal with the language eccentricities most of the time. The C-sharp guideline documents and the blogs and forums have lots of entries about when to use the braces, when it's okay not to, and how to place them in the code. In the Eiffel culture, we believe that programmers' efforts are better spent on understanding the complexities of the problems they're trying to solve, rather than those of their programming language. In this look at Eiffel and C-sharp, I want to concentrate on the things that C-sharp has that Eiffel doesn't have and doesn't need, and why. Remember that often in software, less is more and more is less. Every language feature introduces additional opportunities to foul things up, just like every line of code you write is an opportunity to make an error and adds to your maintenance load. So let's look at some of these language features. Much like most object-oriented languages, C-sharp allows programmers to use the class facility to model classes of real-world objects occurring in a problem domain. But C-sharp also provides several other facilities, as you see here. Each of these has some special programming-oriented purpose and its own set of semantics and rules. Eiffel, on the other hand, has just the class. Now you might think that if this is the case, then Eiffel surely must be at a functional disadvantage as a result. But that's not true. Everything that can be done with all of C-sharp's special purpose facilities can be done with classes in Eiffel. And again, the benefit is that there are fewer things to deal with. The rules are simpler and more clear-cut, and the number and complexity of possible relationships is reduced. Let me give you just one example. A C-sharp interface defines a set of required methods and properties for any class implementing that interface. None of the members of an interface is allowed to have an implementation. So an interface is really just a group of call signatures for methods and names and access modes of properties. But it's a valuable notion because it lets us group together features required to model some concept in software. When a class implements the interface, it must provide an implementation for each member in the interface. So how would you do this in Eiffel? If you guessed with a class, then go stick a gold star on your refrigerator. You'd put the feature definitions along with their contracts, of course, in an Eiffel class. Any class wanting to implement that interface would just inherit from the class that contains the feature definitions. Remember, Eiffel has full, safe, multiple inheritance, so you can just inherit from multiple classes. You don't need a special thing called an interface. And with Eiffel classes and multiple inheritance, if there are reasonable default implementations for some of the features, as we see here with feature B, you can go ahead and include them, and that will probably save some time and duplication of code in the future. Here is one area where more is actually less. Jump statements. C-sharp has 5 different jump statements. Jump statements transfer control from the jump statement to some other target area in the code. Back in the 1960s and 70s, software construction went through a bit of a revolution called structured programming. This is kind of how it got started. Two researchers named Boehm and Jacopini showed that any program, no matter how complex, could be written using only three basic control structures. First, sequence, or one instruction following another. Second, selection, what we know as if structures. And third, iteration, what we know as loops. Then a respected computer scientist named Edgar Dijkstra wrote a letter to the editor of communications of the ACM in which he argued that the go-to statement causes such terrible software quality problems that it should be abolished from all high-level languages. So what this means is that if your language has the three basic control structures, it doesn't need a go-to, and you're probably better off without it. The structured programming message reached most serious software engineers, and the quality of software improved as a result. In fact, most engineers that were programming during that time probably haven't coded a go-to since Green Acres aired in prime time. Inexplicably and unfortunately, language designers kept designing the go-to into their languages. What we see in C# is the go-to in its most obvious form, plus some less obvious versions. You should view statements like break and continue as go-tos in sheep's clothing. In Eiffel, there are no such jump statements. Transfer of control can occur within the three control structures, sequence, selection, and iteration. Each of these constructs is autonomous and has a language mechanism to encapsulate the transfer of control so that explicit use of jump statements is not necessary. In Eiffel, control enters all routines at the top and exits at the end. So it's been clear since the late 60s that the go-to is not just unnecessary, but harmful too. If you accept this, then you'd think there would be no reason ever to use any of these jump statements. Unfortunately, in C# you can't just abandon them because certain language constructs require them. For example, a C# switch statement requires a jump statement at the end of each case to keep control from falling through to the following case. Usually the jump statement used is a break statement, which makes a switch take on this form. In fact, in many C# style guides, the break statement is required fair, which is probably good because it would help prevent this type of convoluted and error-prone but perfectly legal structure. Here, cost is calculated by a switch that has cases in which the jump statement is a go-to carrying control back into the switch at a different case. Looping control is one of the most bug-prone things we do in programming. It was even more bug-prone before languages included special control structures for looping. C# includes four such structures: do, for each in, and while. Do executes a statement or block of statements at least once, and then continually as long as a condition remains true. This type of loop is called post-tested because the loop code is executed at least once before the condition is checked. For executes a statement or block of statements continually until an expression evaluates to false. The syntax for for includes not just the expression, but provides for one or more initialization statements and statements called iterators that get executed at the conclusion of each iteration and should eventually cause the expression to become false. For loops are pre-tested. For each in executes a statement or block for each element in an array or collection. And while is a pre-tested loop that executes a statement or block continually as long as some expression remains true. So it seems that C# has a really rich set of options for iteration. Eiffel, on the other hand, offers only one option. It's the loop construct, and it looks like this. After the from, you code any initialization that needs to be done prior to the loop code being executed. After until, you code an expression which, when true, will cause the loop code no longer to be executed. In the design of Eiffel, a number of language design goals or guidelines were pursued. One of these is called the principle of uniqueness. It says a language should provide one good way of expressing every worthwhile capability. It should avoid providing more than one. So this is the only iterative language construct in Eiffel. You might ask if that's sufficient. That is, can this simple structure do all that the four structures in C# can do? The answer, of course, is yes. For example, how would the Eiffel loop be used to traverse a collection like the C# for each n? Suppose we had a collection of strings and we wanted to append a space onto the end of each string in the collection. It's pretty simple, really. The initialization is used to set the collection's cursor to the first item. The exit condition is exhausted, which means that each collection member has been visited. In the loop code, item refers to the collection item currently under the cursor, and append adds the space. Then the fourth feature advances the cursor to the next item in the collection. Now, having described that, I should tell you that things actually get simpler, and for good reason. As I said earlier, coding a loop is one of programming's most bug-prone activities. Insufficient exit conditions and off-by-one errors are just a couple of the bad things that can happen when we code loops. Because of this, it makes sense that in day-to-day development we code as few loops as possible. One thing that helps is object orientation. If certain classes of objects are likely to require frequent iterative computation, we can encapsulate that behavior in the class and provide, as part of their interface, a straightforward and less error-prone method of getting the iteration done. So here's another way that we can add a space to the end of our strings, this time without coding a loop. Every traversable structure in the Eiffel class libraries supports features for iteration. In this case, we use doAll to apply a feature to every item in the collection. In this case, the feature is the append feature of the string class. What we actually pass as an argument to doAll is just an object. It's called an agent, and it's just a software model of the string class's append routine. There's one more thing I want to tell you about coding iterations. Because they're so troublesome, loops have drawn a lot of attention from researchers. One result of this attention is the development of descriptors for the correctness properties of loops. These descriptors, called loop invariant and loop variant, are an optional part of the loop syntax in Eiffel. You can learn more about loop correctness in the online documentation at Eiffel.com. C# provides at least 3 methods of allowing access by clients to a supplier class's instance data. First is the public instance variable. In this case, the data are marked as public in the supplier class, and a client can just use direct assignment to change the data. Now, this is only okay if any valid value for the type of the data is also valid in any instance. In this case, it's only okay if temperatures of any double floating point value are valid. But suppose here that the validity of an instance depends upon the temperature being between 0 and 100 inclusive. Then the public instance variable is unsafe. So you take the second option, which is what is done in Java and C++. You make the data item itself private, and then you write get and set routines to access the data. The set routine contains some defensive programming to keep from setting the temperature to a bad value. But with this option, a client can't just assign to temperature as with a public instance variable, because the variable has been made private. Rather, it needs to call the set routine to change the value. But C# has a third option, which is not available in C++ or Java, that is, public properties. A public property looks like a public instance variable, except that properties can contain get and set routines, but no data. The data that the property gets and sets is ordinarily private. So here the get routine returns the internal private temperature value, and the set routine does the checking to make sure that the value the client wants to set is valid. Incidentally, value is a C# keyword for property set routines. With properties, you don't actually call the get and set routines. You just use the property name as if it were a public instance variable, and the appropriate routine gets executed. So in the client class, this looks like assigning directly to the property, but it's actually invoking the property's set routine. Now what about Eiffel? In Eiffel, you expose member data through public attributes. Don't confuse the term attribute as used here with .NET attributes. In Eiffel, an attribute is like an instance variable in C#. So here, in the supplier class, we would have the declaration for temperature. Now you might think that since temperature is public, we would have the same problem as with the public instance variables in C#. That is, a client could contain code like this. But this problem doesn't exist in Eiffel because statements like this always generate a syntax error in Eiffel. Clients can't assign to member data. They can read it, but to change it, they call a set procedure like this. So what does a set procedure look like? Well, it's different from the ones that we've seen in C# in an important way. It contains a contract. The contract is a declarative description of what it means for this routine to work correctly. So it says in the require clause that the client must provide a value between 0 and 100 inclusive. The insurer says that if the stuff in the require is true, then when the routine gets done, it will have set the temperature to the value passed by the client. The effect of the contract goes much deeper, but that's all I'm going to say here. If you haven't seen the Design by Contract presentations, I'd recommend that you do. Let's look at one more aspect of access to instance data. How is the accessibility to certain instance variables in C# declared? Well, it's done by adding modifiers to the individual declarations as we saw in the previous slide when we changed temperature's accessibility from public to private. C# provides 4 unique access modifiers plus one that's a combination of 2 of the others. The rules governing the use of these modifiers with classes, structs, interfaces, etc. get complicated, and I won't try to go into those now. But let's just look at the meaning of the 3 modifiers most often used. A public modifier means that access to this member is not limited in any way, so clients and heirs to a class can access its public members. Protected means that access is limited to the class in which the member is declared, or any class or type that derives, that is, inherits from this class. In other words, clients can't access, but heirs can. And private means access only by the type in which the member is declared. How is Eiffel different? To begin with, in Eiffel, access is only restricted in any way to a class's clients. So heir classes can always have access to all features. In a minute, I'll explain why this would be a problem in C# and why it's not a problem in Eiffel. But first, let's look at the mechanism for allowing access to clients. In an Eiffel class, features are members in Eiffel speak, are organized under feature clauses. Each feature clause has the option of specifying which clients can access the features under the feature clause. Here's how it works. Let's look at a hypothetical class called A. Under the first feature clause are features F and G. Notice that the feature clause is followed by the word any enclosed in braces. What this means is that features F and G are available to clients of any class. Now it turns out that what's enclosed in the braces is actually a list of class names, and the features are accessible to clients based on any of the classes within the braces as well as their descendants. In this case, there's only one name, any, which happens to be the class from which all other classes inherit. In Eiffel, we say these features are exported to any, which means about the same as saying that they're public. Now I've shown you this in a way that illustrates the class list, but actually if you leave the class list off, it's the same as coding any in the class list. So usually we show public features under a feature clause with no class list, like this. So how do we code features that are only available to the declaring class? Well, like this. Here, none is a class from which no other class can inherit. So in this case, feature H is exported to no client classes, but is available within the class A and its heirs. What really makes this technique interesting is that you can control access with far more granularity in Eiffel than in other languages. Here's an example. Feature J is available to classes based on classes B and C and their descendants, but to no others. So this works well for helper-type classes, the cases in which one might choose to use a nested class in C#. And while we're on the subject, nested classes are another feature of C# that's not available in Eiffel. One reason is what I just said. The granularity of export in Eiffel is fine enough to eliminate the need to use a nested class just to get access to otherwise private data. Another reason with more far-reaching consequences is cultural in nature. Making a class nested absolutely ensures that it will never evolve into a reusable software asset. In the Eiffel culture, even if we don't see any possible way that a class may be reused, we try not to impose that prejudice on those who come after us. Now earlier I promised to give you an explanation of why Eiffel doesn't need to restrict access of features to heirs, as C# does by using private. You can hear the full explanation in the Design by Contract presentations, but for now here's the short version. The reason in C# you'd want to restrict an heir's access to instance data is that the producer of an heir class might write some code in that heir class that would create invalid instances of the class at runtime. Likewise, with routines, you might not want to allow certain inherited routines to be overridable, because heirs could be created with misbehaving versions of the routines. This is such a problem that for security reasons, some classes are sealed off so that you can't build an heir to them at all. But these problems don't exist in Eiffel because of Design by Contract. The class invariant that you code defines what it means for an instance to be valid. Each routine has a contract that specifies its behavior. And all those contracts are inherited and must be adhered to by heir classes. So all the heir code must work in compliance with the contract that the class inherits. Of course, heir classes can add to the contract as they add to the class. Then this new fuller contract gets passed to their heirs, and so forth. So this leaves us with another list of features of C#, including private members and sealed classes that aren't in Eiffel because they don't need to be there. Another thing that C# inherited from C is the main routine. The main routine is just the initial entry point into a software system. As a result, each executable system has one and only one main routine. Eiffel systems have one and only one entry point as well. It's a procedure in one of the system's classes, and it's called a root procedure. There's an important technical difference between a C# main routine and an Eiffel root procedure, but there are even more important philosophical or perhaps even psychological differences. Let's take the technical difference first. In C#, the main routine is coded in a class and recognized by name by the C# compiler as the entry point for the system. In Eiffel, the root class is one of the classes in the system, and the root procedure is one of that class's creation procedures. Creation procedures in Eiffel are roughly equivalent to constructors in C#. So when an Eiffel system starts, a single instance of the root class is created, and the root procedure is applied to that instance. The important technical difference between these two approaches is that there is nothing in the Eiffel code that indicates which class is the root class and which procedure is the root procedure. That information is stored separately from the code, and it's used by the compiler when it creates the executable system. What this means is that a class that's the root class in one system is freely reusable without modification in another system in which it's not the root class. This is not the case in C#. If you want to reuse the class with the main in another system which already has a main, then you have to maintain two versions of the class. I heard from one C# programmer that his organization's policy dictates that the only thing that a class containing main is allowed to do is to create a single instance of some class and apply a constructor. I think this is good because it shows that the organization recognizes the problem and it's taken steps to work around it. But what about the philosophical differences? It boils down to this. The main routine is a holdover from days before object-oriented programming. At that time, we used a technique called functional decomposition, in which the goal was to create things called programs. Each program had a main or top routine, which called other routines, etc. So we designed things from the top down. In object-oriented programming, we tend to think of creating systems rather than programs. These systems are usually constructed by combining a lot of previously created components, classes that is, with a few newly created ones. So the best object-oriented programmers view the process of programming as that of assembling components into a system. Having a main routine can have the psychological effect of keeping us back in the top-down, program-oriented world, where a program would be designed from the main downward. And this mindset conflicts somewhat with the goals of reuse that are made possible through object orientation. Well, I know that's been a lot to digest in a short amount of time. I think maybe the most important points for you to take with you are these. Microsoft.NET is an important step forward in software technology, particularly in the area of programming language interactivity. C# is a programming language based on C and specifically designed to address the .NET object model. C# omits some of the troublesome features of C and C++. Still, in the name of familiarity, it carries lots of inelegant baggage from 30 years ago into the present day. Eiffel was designed from the ground up to be simple, elegant, and powerful. It's based on a pure object-oriented model with facilities for full, safe, controllable multiple inheritance, and designed by contract, even in the Microsoft.NET environment where these capabilities are not part of the native object model. Additionally, these facilities allow Eiffel to omit many of the complexities that are necessary in C#. I hope you've enjoyed this presentation and found it informative. Thanks for tuning in.